Good, 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 good. We have 4 people. All right. Uh, I'm going to get started. First off, I'm glad you're here. Happy New Year for those of you uh, who haven't been around for a while because of the New Year's, obviously. Tonight is going to be a very special night. Okay, we're going to be working on open-ended problems. Okay, so what does that mean? Or open-ended problems. Open-ended problems, right? First off, we're not going to do any lectures or any exam material, which is usually covered for students when it comes to, like a lot of YouTube videos. Tonight's going to be very different. It's going to be on open-ended problems. Okay, just 1 second. Someone's giving. Right. So the goal is going to be very specific. We're going to be looking at problems that don't have one specific solution. First off, okay, and that aren't obvious to solve, right? So if you're used to problems that have, some sort of algorithmic way to solve them, uh, a very easy, not very easy, but a somewhat predictable way of knowing what method to use in a straightforward fashion, tonight is very different. We're not going to be doing that, okay? This is going to teach you how to solve problems that aren't obvious to solve. Okay, so we're going to be pushing the borders of our reasoning abilities tonight, and mine too. Okay, all right, so 1 second, someone's trying to get into it. All right, so first off, right, in real math and science and engineering, I'm sure it's the same thing. Quite often, the problems don't follow an algorithmic approach to solving them. Okay, usually in the real world, things aren't ideal, so the problems need to be broken down using non-elementary techniques. Okay, and that's what we're going to be looking at tonight. Right. Okay, I just want to see if anyone else is coming in. If I should continue, see if anyone else is coming in. Right, nothing yet. Let me see. Right. So here's how this session is going to go down. Okay. First off, there's 3 things I want to point out when it comes to doing a section like this. Okay. First off is that don't worry about getting the problem right away. Okay, when it comes to open-ended problems. Okay? Quite often they can be frustrating. Right? Sometimes very frustrating. Okay, sometimes you're just going to be stuck there looking at a problem and saying, "What the hell is this?" Right. So first off, don't worry about getting the problem correct on the first try. Quite often you need to test a bunch of different techniques or methods in order for it to start working. Okay, so that's number 1. Just 1 second, sounds great. And also, don't worry about the speed. Okay, I know that sounds a bit weird because quite often everything is speed, especially in school and university. However, though, when it comes to open-ended problems, you're going to be you're only going to see them either if something that you want to look at yourself, if you're interested in doing it yourself. They won't be on an exam, more likely not, unless your professor just tries to trick you and do stuff like that. There's a few professors like that, but they're very rare. But yeah, those professors do exist, right? So first off, don't worry about speed. Okay, so don't worry about speed. Don't worry about getting the problem right on the first batch or second batch or second try, whatever you want to call it. Okay. Right. And number 3, which is very important when it comes to doing this. Hello, Blazing. Hello. Blazing, what brings you here? Are you interested in advanced mathematics, physics, or any of those things? Or are you a computer science student? Just curious. I'm good. I am good. I hope you're doing well. So tell me about yourself. Are you a student of some sort? Okay, yeah. Well, what do you take? Is it computer science or what? I notice I get a lot of computer science and engineering guys. Some math, not really, but that's what we need. So we need. Oh, really? Okay. Oh, perfect. All right. So I assume what you need, like integration, I'm assuming, right? Or some form of calculus. That's PCM. Okay. Yes. Okay, perfect. Yes, we're going to go through this. Yes. I'm glad you are interested. Are you taking, I know you said you need this. Can you tell me what course you're taking at the moment, like specifically math based, what you're taking? I'm just curious. Okay, you know a bit. All right. Uh, well, guess what? There's a lot to learn when it comes to calculus. So I hope you will enjoy this live show. I'm just getting started. Always at the beginning, I have to talk a bit, and I don't want people just to like, okay, he's going right to the board and not know what's going on. Oh, nice, physics, math, and chemistry 11. Beautiful. I love all three, and I took all three when I was in high school. Perfect, perfect. Okay, so yes, this live show is going to be very interesting, right? So I'm just going to bring up some things that are important, right? This is a live show that is very unique. Normally, I do my shows on either, you know, they're usually regular lectures. Okay, good. Okay. Now this right now is not specifically for the JEE. However, though, the thinking process is the same. Right? So the thinking process, even if you don't know exactly what I'm doing, because this is advanced, you will see how it's going to help you for the JEE. Okay, it will actually help because it's going to push the borders of your thinking process. Okay. So it's going to, yeah. That's what matters at the end. It's not always the specific topic. It's it's supposed to help structure your way of thinking, right, with some clarity. Okay. So I'm going to do my very best to help you on that. Okay. If you have resources, you can always check whilst I'm talking. If you're not understanding the nomenclature I'm using, or some phrases. I will explain, but a lot of it will require some background, but it's okay. I think you'll be able to understand, right? For the most part. Okay, good. All right. Okay, so good, excellent. That's what I want to. Good, good. All right, let's go to the whiteboard if possible. Okay. All right, so let's share the screen. I'm going to share screen. Okay, so just 1 second. Let's share screen. Okay, and we're going to go to the whiteboard. All right. So if you look at the whiteboard right now, right? Okay. So as I mentioned, it's going to be open problems today. Now, let me get into more of an in-depth, uh, you know, definition-wise of what an open problem is. Do you understand what an open problem is? Oh, so do you know what an open problem is, by the way? I'm just asking to see if you know what it means. Just let me know if you know what an open problem is. Blazing. So an open problem, yeah. Can you explain? I'm curious because in a live show, what's going to be very beneficial is if you can also. I'm going to ask you questions as well. Okay, right? Because it's really it's going to really help you actually to validate certain things back and forth. Oh, just another internet guy. Nice to see you. Perfect. I'm glad you're back. Happy New Year, by the way, to all of you. You're always the top student that comes here. She always gets all the questions right. So I'm glad you're back, just another internet guy. Yeah. Okay. Yeah. So, Blazing, you were saying, what is your so what's the definition of an open problem? Can you tell us? Can you tell everybody what an open problem is? It will be handy. So, what is an open problem per se? Yes. Okay, good. I'm surprised you know that. It's very good that you do know that. Yes, that's exactly what it is. It's a problem in which either it has a definite solution, but it has multiple paths, multiple ways of getting to a solution. Okay, either that or it requires immense amount of creativity to solve. Okay, or number three, there doesn't seem to be a known solution at the moment. Okay, we do know that there is some solution. We don't know what it is exactly. Okay, so that's what an open problem is. Okay, now some of these are very tough. Uh, However, though, they are fun though to solve. Especially, I'm going to give you a toolkit to approach them. I've done these before, and they are a headache. Okay, we're going to probably look at one, maybe two, maybe two, but more likely one because they're annoying. Okay, so this will take up some time. All right. And also, I'm going to be using some simulations to show you geometrically what is happening to the function as well that we're trying to solve. Okay. Right. So let's get back to it. Okay. So let's get started. All right. So what we're going to look at first problem is we're going to try to solve this problem right here. Okay. And if you all know this, I know just another internet guy knows what this is called. This is an integral. This is an improper integral of cosine of ax with respect to x, all divided by 1 plus x to the 4, and we're expected to integrate this problem. Okay. So, Blazing, if you want, you can try this guy here. By the way, this is a serious monster, if you've noticed. Any ideas? Cosine of ax with respect to x divided by 1 plus x to the 4. And take your time. It's not about speed. These problems require some type of, clear thinking to solve. Just 1 second. Just have to. Someone is sending me something. Yeah. Now, just another internet guy is right. We can use Feynman trick on this. That's one way to solve it. There's two ways to solve this: either using Feynman trick, or you can use contour integration. Okay. All right. So either path will be able to solve this problem. Okay. Now, I'm also going to write it like this. I'm going to call I as a function of A for obvious reasons, just to make things easier. I as a function of A. We'll sign down here. Okay. And I made it as a function of A because just another internet guy probably knows what we're supposed to do. Just another internet guy. What do we need to do on this integral? Blazing. Now, when you mean chain rule, can you be more specific with chain rule? What do you mean? you can type in the chat there. You need to apply chain rule. Not quite. I don't know what you mean by chain rule. Are you talking about the derivative with the chain rule? And with respect to what? Because that might be a bit problematic. You're getting some or something. Yeah. So Blazing, if you were to use the chain rule, I assume you mean something like this. I'm going to write on the side over here, just to remind everybody, chain rule. Let's say you have f as a function of g of x, and I took its derivative. This would just be f prime of g of x times g prime of x. Is this what you mean? Because this would not be it, right? This wouldn't help us really per se. Right? It won't really give us. Yeah. Yes, just under the guy got it right with respect to A. Yes, because we want to use Feynman trick. Blazing, are you familiar with Feynman trick? It's okay if you're not. They don't teach it in standard classes. Blazing? Have you learned Feynman trick? I just want to make sure that you sort of have an idea what just the guy is recommending. Right? We're going to use Feynman trick on the integral, right? Okay. So Feynman trick. Okay, so I'm going to use Feynman trick. Let me know if you're not understanding something, Blazing. All right, so Feynman trick states the following. I can differentiate both sides of the integral. So I'm going to do here with respect to A. So this would be I prime. Okay, so I prime as a function of A, right? I'm differentiating with respect to A. And this is equal to, I'm just going to use over here, a different color, D by dA. Okay, parentheses. And then I'm going to integrate from 0 to infinity of cosine of AX dx. Just 1 second. My coloring isn't as good here. Cosine of AX dx all over 1 plus x to the 4. Okay, you understand what I'm doing? I'm using using Feynman trick and differentiation under the integral sign. Okay, so I'm going to say by, this is, okay, so this is by Feynman, this putting the justification here. And this is by Feynman trick. Just 1 second. It's by, 1 second. By Feynman trick. Feynman trick. Okay. You see, Blazing, if you understand. The f of g, this is what I mean. Yeah, but we're not going to be using per se that unless what you mean. You see, you have to be careful. You have to be able to differentiate and explain what you mean by what derivative rule you want to use, right? And why you're using it. Was there a reason why you said chain rule for this integral? And with respect to what? Because remember, there's two variables. We have a and an x here. Oh, no. Okay. Getting some internet issues? Damn, I hate when that happens. Okay. Yes, if it's a problem right now, please watch it later. This will be very beneficial. And at the same time, whilst you're watching it, I want you to pull up on my YouTube channel. You can find another lecture where I'm talking about either Feynman trick or contour integration, especially if you haven't done this before. So refer to other resources on Feynman trick and you understand why I'm doing this, okay? Justin Arena guy has a strong background and he already knows he's seen my other lecture, so he knows what I'm doing. Okay, so Blazing, please do that. That'll be handy. Okay. All right, so we've got the I prime of A. Okay, and then what we're going to do, obviously, just move this inside. I prime of A. Okay, and this is going to be equal to the integral from 0 to infinity. I'm going to say d by dA inside of my integral here. Right? It's just differentiating under the integral sign, okay, of cosine AX dx. Okay, I'll put a dx outside here somewhere. Oh, I could put it over here, doesn't matter. Dx all over, we have the 1 plus x to the 4. Okay. So this is what we have right now. I want to move my dx down here just 1 second so anyone can see it. Yeah, integrate with respect to x, okay? Using chain rule and cosine x, I guess because a is the problem. No, that's not where, no. There's no chain rule. Yeah. See, oh, I think I know what you mean. You were treating the cosine of ax. Okay, I see what you're saying. Cosine of ax. Yeah, I see what you're saying. So you're saying out here, the cosine is your f, right? And the inside function, ax, is your g of x. I think that's what you meant. Something like this. And then you wanted to take the derivative. But okay, yes. But how do you know that we have to take the derivative in the first place for this integral? What made you say that in the first place? Right, that has to be a reason. All right, perfect, Blazing. I'm glad you're going to watch it later. Sorry that you're having internet connection problems. Please watch it later, but also look at other resources, especially my YouTube channels. YouTube channel have a video on Feynman trick for the definition and formula, so you better understand why I'm differentiating both sides of the integral. Okay. All right, and how I can interchange it. First off, over here. All right. And don't forget to like and subscribe. That'll be handy. So back to the integral, right? Over here, right, I can move the differential, the derivative under the integral sign, right? So I'm just saying here, moving. This is by interchanging the integral with the derivative, the derivative. Okay, so that's what I'm doing right now. All right, so that's the first thing. So right now we have this. Now from here, how do we differentiate this? Okay, so we have, how are we going to differentiate our function inside of the integral sign with respect to a? How do I differentiate with respect to a of the function? Anyone know how to differentiate with respect to a of the function? It's going to be x, negative x sine x, okay? Because if you differentiate cosine, it would be negative. So, and then after differentiating with respect to a, x is constant, so it becomes negative x sine of ax. Then we have their dx. I'll take my a's, look better. ax dx all over 1 plus x to the 4. Okay. All right. Let me know, guys, if everything is making sense here. Right, so this is what we have so far for our I prime of A, right? Our derivative or integral. by Feynman trick, and otherwise known as also part of Leibniz rule differentiating both under the integral sign. Okay. All right, so now we've got this. I can move the negative in front. I think it just makes it more handy. Okay, it makes it look better. So I prime of A, okay, is equal to negative. Okay, so negative the integral. Okay, so negative integral from 0 to infinity. Okay, of x sine of ax. A's look like u's. Ax dx all over 1 plus x to the 4. Any questions? Who has questions so far? Now, I just want to let you guys know that as we're solving this right now, I do know that it does have a solution to this integral. Okay, so there is a solution to this integral. It just has multiple ways of getting there, and those multiple ways can be a bit tricky. Okay, probably contour integration would have been easier to solve this, but we're using Feynman trick as recommended by just the internet guy. Okay, now we do reach a bit of an issue. Okay, if you noticed, we did differentiate under the integral sign, and then after our expressions should be able to be integrated after we've differentiated. Problem is, you look at the integral, we have an issue. How do we integrate that? For all you calculus guys out there that you've never seen this type of integral before. That's right. Integration is much harder than what you've been seeing. Okay. So we have to, we need to think a bit out of the box. Okay. All right. So how do we solve this? How can we integrate this? I want to use a different color. This. Anyone have any ideas? I want your input, guys. Okay. How do we integrate that? Just 1 second. Someone give me a thing. How can we integrate this monstrosity? Anyone know? Just another guy. Have any ideas? Anybody have any ideas? How can we integrate this? Yeah, I know it looks intimidating, doesn't it? Okay. There is a way to do this. Okay, but you'll notice that we can't integrate right now. Okay, so by Feynman trick, if you watch my other, streams or live shows, I talk about the definition, right? You're supposed to input a parameter alpha in that's your function of parameter alpha, right? And your alpha has to be placed in the correct location of your function such that when you differentiate both sides by Leibniz differentiation under the integral sign, you can then integrate afterwards. Okay, that's normally the first part of what the theorem says. Okay. However, though, if you're not able to integrate, you can do something special. Unless someone wants to take a guess, I'd be impressed if you can figure it out. I haven't talked about it in before though. I know everyone's getting intimidated by this. The x sign of ax over 1 plus x to the 4. How do you integrate that? So again, right? We can't integrate that because there's no elementary methods that will work. Even complex methods, advanced methods won't work either, right? Like what I mean by that is if you were to use, some other method outside Feynman trick, it won't work. Okay? So we have to keep using Feynman trick until we're able to integrate the function. So what I mean is we found the first derivative with respect to parameter a, okay, on both sides. Normally after the first derivative with respect to a, we should be able to integrate with respect to x. However, though, we can't. Okay, you notice obviously you can't solve that. Integrating is just broken. It doesn't go anywhere. Okay, so what I need to do is I need to differentiate. Again, yes, I can use the Feynman trick n number of times, differentiating with respect to n number of times until I'm able to integrate with respect to x. Okay, that's the way to do it. Okay, so we have to see how many times we have to differentiate with respect to a. Okay, so this would be I prime. Okay, so this would be, we found I prime of a. Let's find I double prime of a. Okay, and this is going to be negative. Okay, negative the integral. Okay, negative integral from 0 to infinity. Okay. Okay. Of well, I'm differentiating with respect to a again. So what that means is this, I can pull out another x. This becomes x squared, right? And I'm differentiating the sign of ax because it's with respect to a. So this becomes x squared cosine of ax dx divided by 1 plus x to the 4. Okay. That's what we've got right now. All right. Please let me know in the chat, a thumbs up if you're understanding. If you're enjoying the live show, please put capital F for Feynman. Yes, sounds contradictory. Just put an F for enjoyment, but maybe I should have said E. Right, so this is what we have so far. So this is really interesting. A lot of times people think for very complicated integrals that they're completely unsolvable. Yes, that is true because elementary methods don't work. However, they can be solved still using very complicated methods. There's so complicated methods that exist to solve them. However, the next problem we're going to look at doesn't have any solution whatsoever. Okay, let me see what this. All right, so right now we have this integral, right? I differentiated the second time with respect to a, okay, because we weren't able to integrate right away after using from the Feynman trick, differentiating with respect to the parameter a. Okay, so this is what we have right now. Okay, we have this monstrosity. Now, we still have a bit of a situation. Okay. I am going to do something here. Let's see what I'm going to do. 0, 0, thing collapses. Yeah, I may have to do that. So we have I prime of a, and then we have I double prime of a. Okay. Now, we're having a bit of an issue. The more I differentiate, the more complicated my integral gets, as you can see here. Okay. Oh, Patrick Charlotte, thank you for joining. Remain, so I will save it. Yes, please save it. This will be very handy. Yeah, because this will help for JE Advanced. Okay, so please, I want you to watch this whole the whole video if you can, because it'll be really handy. Okay, so please watch it, and please also subscribe. That'll be handy. You can subscribe, like and subscribe to the channel. Okay. Thank you, Patrick. Thank you for joining. I really appreciate it. Okay, really appreciate it. All right, so right now we've got this, and it'll be really handy. You're going to learn a lot of different techniques on how to do, things like calculus and ODE stuff like that, especially integral calculus. Okay. All right, so we're looking at I double prime of A, right? So this integral right here looks nasty, okay? So as I said, again, for those of you coming in, what I've done is I have an integral as a function of A with a parameter A there. Automatically, it's in the form of a Feynman trig integral, okay? So, right, this is a Feynman trig integral right over here. I'm going to highlight what this is. It's a Feynman trig integral, okay? What I'm pointing to, okay, right there. Then what I did, again, I'm reiterating, I differentiated both sides with respect to parameter A. That's just a mixture of Feynman trig with Leibniz differentiation under the integral sign with the parameter with respect to parameter A. Okay. Right. And then what I did is when I differentiated, okay, I was not able to still, because after when you differentiate both sides with respect to the parameter A, you should be able to integrate with respect to X. Unfortunately, we're not able to do that. Okay. So by Feynman trig, what I can do is I can differentiate my integral I that I've defined as A, as a function of A, n number of times until I figure out a way to get past this monstrosity of an integral. Okay. All right. So that's what we're doing right now. Okay. So we have the I double prime of A. Okay. Anyone have ideas of how we can go past this? How can we get past this nasty integral? Because you have to admit, it is nasty. Right down here, this is where we're having our issue, okay? You have to integrate I double prime of A, okay? I double prime of A is equal to this negative integral, improper integral of x squared cosine of ax dx over 1 plus x to the 4. Now, some of you may be thinking, how do you do that? Yes, how do we do that? Because the more we differentiate, the more complicated it's getting. Okay. However, though, we need to solve this problem, we have to keep differentiating. Okay. I think there will be a pattern that will be able to come out of this, right? So I triple prime as a function of A now. Okay. Okay, so this is going to be if I differentiate with respect to A. Okay. What will happen here is I'm getting negative integral from 0 to infinity, okay, of differentiate with respect to A. This cosine now, okay, becomes negative sine, and the A gets, the X gets pulled out because we differentiate with respect to A. So this becomes negative X cubed of sine of AX, okay, all over 1 plus x to the 4 dx, okay? This is after doing I triple prime of A. All right, any questions? We've got a lot of people preparing for the JEE exam, so this is going to be good. Glad that you're finding this handy. Also, if you're not understanding something, for those of you who want to watch later, please refer. If you're not here right now, I'm just going to say it in the live show. If you haven't seen some of the methods I'm using, please refer to one of the other streams or live shows on my YouTube channel. So look for the one that says Feynman trig. It's a full stream about the definition of the Feynman trig, in how Feynman trig integrals look like. And then from there, step 2, all the steps you have to do. in order to integrate a really advanced integral, okay? Because they do pop up. It's not like they don't. Complicated integrals can pop up, especially if you're doing a JEE advanced or some type of advanced Putnam/Olympiad problem. They may put a calculus problem. Usually, it will be an integral or a series. At least one of them. The rest of them are not related, but yeah, they come in handy knowing these things. Okay, so looking at I triple prime of A. First off, move the negative to the front. So this is going to become I triple prime of A equals positive, right? The integral from 0 to infinity, okay, of x cubed sine of ax with respect to x all over 1 plus x to the 4, okay? Because it's negative, negative becomes positive, all right? This is what we have. Okay. I would like someone to guide me through what we should do with this. Just 1 second. Just give me a moment. Someone is saying me something. It'd be good if I get input from the audience. Okay. How can we integrate? How can we solve this integral of x cubed sine ax with respect to x all over 1 plus x to the 4? How do we do that? If anybody knows. Let's see if anyone knows. How are we going to integrate this? Right now, you can see our integral is getting more annoying, right? How are we going to do that? See, our integral here is a bit of an issue. I'll give you some time, maybe 2 minutes or something. If someone can offer their a view of how to solve this. What we did is we decided to use the Feynman trig approach because we saw that our original integral was a function of a parameter a. So it's written in terms of a Feynman integral, okay? Please let me know what you think. Yeah. See that our integral, right, is not a standard integral that you're used to in your classes, right? Even in university, sometimes these things may trip people up. It's not as straightforward. Right? So if you look at this, one way to do it, okay? Right, so one way to do it is to notice something interesting here, okay? So how can we integrate this bugger? I am going to leave that for you guys to figure out, okay? I want you guys to be able to figure out how we would solve this using a Feynman trig, okay? Right? So I'm going to leave a hint here, okay? Hint will be, okay, hint is, here's the hint. Use a mixture of Feynman, so you continue, right? So continue using this approach above, approach above, approach above, with with something called with boundary conditions, or it's a boundary conditions. You should know what boundary conditions are. Boundary conditions. Let's say, for instance, just 1 second. I at 0 equals, let's say 1, for instance, something like that, and so on, right? So you have to use boundary conditions. What that means is that at a, our parameter a will be defined as some number, and then our entire function of the integral at a is equal to a number. Okay, so you're going to need to use boundary conditions to solve this. Okay. If you've watched, and the reason why I want to give it for homework is, and not for me to do it, so that's why you can see how to challenge yourself, right? How to really push the boundaries of your thinking in this. Because I do have another a lecture on Feynman trick. So I feel like if you understand it really, the theory really deeply, and then apply it, you should be able to solve this yourself. That's the trick here. Pun is trick. Okay. So please do this part for homework. So let's say I have 0 is 1, or I have 0. If it is I have 0 is equal to 0. Well, one of those works. Can't remember how I solved it. I have 0 is equal to 1, or I have 0 is equal to 0. Okay. So that one I want you guys to finish up for homework. Okay. All right. And there's also multiple ways of doing this. You could either have used this method, okay, the Feynman trick, or you could have used something called contour integration. Okay, it's up to you, right? Just to let you know, contour integration would be faster. It's still annoying, trust me. Contour integration will be faster. You apply a correct contour, you find your holes and stuff like that. It makes it easier, but it's still an annoying mess. But for Feynman trick, it gets really annoying. Okay, as you can see here, we have to keep differentiating again and again with respect to the parameter a. So it gets really annoying. Okay, but between this or a contour integration, okay, I should say this is approach 1. Okay, approach 1 would have been. So I'm going to write here, this is approach 1. Okay, so problem 1, approach 1. Okay, approach 1. I'm also going to show you another approach to do this using contour integration. Okay, where's the contour? Where's the contour integration? Problem 1. Approach 2 now, right? For the same thing. Let's say approach. Maybe I have to make some room over here. I'm going to try and make room. Okay, so approach number 2. Approach number 2, we're going to do is something called contour integration. Again, if you're not understanding what I'm doing, go look at both YouTube lectures, one on Feynman trick, one on contour integration, to understand the theory really well, and then come back to solving this. Okay, so again, we had our integral was this: I as a function of a is equal to the integral from 0 to infinity of cosine of ax dx divided by 1 plus x to the 4. Okay. Now, by contour integration, right, it's just integrating along some trajectory or some path. Okay. And it's in the complex space. It's in the complex numbers. So, for instance, I is a function of a. Okay. So I is a function of a can now be equal to, right? Can now be equal to the integral from 0, right? So integrate from 0 to infinity of cosine as a function of az with respect to z all over 1 plus z to the 4. So what I did is I transposed. I'm allowed to transpose from the real numbers to the complex numbers. Okay, that's what I did here. So I'm pointing down here. I have, I went to the from the real numbers to the complex numbers. Okay, so now we're in the complex numbers. So imagine the real and imaginary lines. Okay, and the contour that we need to choose here that works for this would be a semicircle. Okay, so what we do is we cut a negative r here and a positive r, right? And a semicircle has radius r, plus or minus r for depending what part of the semicircle. Okay, and then after what we have, remember this is the real axis. The x-axis is the real axis. Okay, so this is the real axis in terms of z. This is the imaginary. It's a function of z. Let me make sure you guys are all there. Okay, so real and imaginary. Okay, then what we've got is, since we're choosing an upper semicircle, okay, you have to be able to know when you're choosing what type of contour. Okay, so depending on what it is, you want to choose a semicircle, upper semicircle, lower semicircle, or a rectangle, or a key, some sort of key type shaped key node shaped for evaluating your contour. Okay, so negative r to r. So we span from negative r to r. Okay, and we have this line here that is collinear to the real axis. Okay, so I'm just putting over here, and it travels from minus r to r. Okay, and then it travels upwards like this. Okay, because it's a semicircle. My semicircle is better. Okay, so something like this. Make my semicircles better. Minus r to r, and it moves in a counterclockwise fashion on the upper arc of the semicircle. Okay, I'll call this C. Okay, this is going to be called C. C for contour. Okay, so capital C for the contour that was chosen. Okay. All right. So the way we're going to be able to integrate this, okay, so let me just put this, and this would be saying from, let me just erase this part. To be accurate, since we're on C, I'm saying I'm integrating over C. Okay, integrate over C. That's the correct notation. Made a mistake there. I'm integrating over the contour of some sort of contour, okay, of our function cosine of AZ, dz all over 1 plus z to the 4. Now, what I can do here is, right, what I can do here is I can immediately do something very interesting, okay? And what that is I can take the following. I can take I as a function of A, and then say that this is equal to the integral, right, all over C of E. I'm going to highlight this with a different color for a certain reason. E to the power of I A Z, right, all over 1 plus z to the 4 with respect to z. Okay. Anyone have any ideas where the e to the IAZ came from? Okay. You can see here I have an integral over my contour, and my cosine is gone. I put e to the IAZ over 1 plus z to the 4 with respect to z. Where did the e come from? Where did that e come from? Think of Euler's identity, because that's what it is. We're using Euler's identity. Okay, so using, I'm just going to put over here, using, this is the justification for this. Okay, this is, I'm going to say here, this is taking the real part, okay, the real, the real part. I'm saying the real part, of Euler's identity. Okay, so of Euler's identity. So of Euler's, 1 second, of Euler's identity. Euler's identity. Okay, and you should know what Euler's identity is. So anyone can put it down here, what Euler's identity is. Anyone know what Euler's identity is? Real part. I want to use not white. I was just emphasizing with a different color of Euler's identity. Of Euler's identity. Okay, Euler's identity, just to jog your memories, right? Z equals e to the I theta. Okay, so Z, Z is equal to e to the I theta. So Z equals e to the I theta, where e to the I theta is just cosine of theta plus I sine theta. Okay. I'm taking the real part of it, of the cosine of AZ, replace e to the I AZ. Okay. Now, what we're supposed to do here when doing a problem like this on contour integration, we look for the holes in the singular, the poles and the singularities. So what you do is you want to focus on the denominator. The singularity is 1 plus z to the 4. So set 1 plus z to the 4, right? 1 plus z to the 4 equal to 0. Okay, and then you get z to the 4 is equal to -1. But z to the 4, okay, z to the 4, right, if we take that and we take this equal to the 4th root of -1, well, -1, first off, is going to be I. Okay. And obviously, if you take the square roots on both sides, you're going to get I. All right. Unless there's any type of any questions or any disputes on that, right? Because I have to take the root on both sides, -1. Can't take the square root of -1, so it's going to be I, right? A negative number. Okay, any questions on that? Anyone has questions? Any questions at all? Just want to make sure that you guys are on the same page. Because if one of you is and then the other guys aren't, then it's just, that's not good. I still need to repeat what I'm doing. So that's why we're all like consistent. Okay. So what ends up happening here, right? You should be having something of the form z to the 4. Now, first off, just want to notice something here. We have z to the 4 equals -1. Okay, so z to the 4 is -1. Just 1 sec. We got someone come asking me a question. Just 1 second, guys. So z to the 4 is -1. I want you to think about that, how we're going to deal with an equation like that. Okay. Someone's contacting me here. How do we solve that? How could we solve z to the 4 is equal to -1? Remember, we know that we're using Euler's identity. E to the I theta is equal to cos theta plus I sine theta, right? A little simple, right? Hint, hint. Right? Since we're using z equals e to the I theta, right? What we're going to say here, right? We know that if we take the fourth root on both sides, z, right, would have to be -1 to the 1/4, first off, okay? All right. That's the first thing. I'm going to continue over here, okay? Then what we're going to put over here is if z is equal to -1 to the 1/4, right? That's after solving for the roots of z, okay? We get something interesting. I can say that -1 is equal to e to the 2k pi, e to the whole power of 2k pi plus I theta. E to 2k pi plus I pi. Yeah, e to the 2. So -1, what you'll get is -1 is equal to e to the 2k pi. I'm going to explain what that is. 2k pi plus I pi, where theta is pi. Okay. So theta is automatically pi, and where k is an integer. Right, k is an integer. Right, so where k, I'm going to put over here where k belongs to z. Right, where k belongs to z, and k is equal to 0, 1, 2, dot, 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 all the way up to n minus 1. Okay. All right, so that's what we should have in that spot there. Okay. And then what we need to do is evaluate for each k value from 0 to, let me be having here, 0 to 3, right? Because n in this case was 4, because the nth power was 4. So we have up to 3. So we have to do k equals 0, 1, 2, 3 to be specific, because it's n minus 1, where n was 4. So 3. And then what we're going to do is input it, right? So we get e to the I pi, k is 0, e to the I pi, right? Any questions on that so far? Okay. So we've got k, right? So for k equals 0, right? Oh, right. I think I almost forgot something. This would be e to the 2k pi plus I pi all to the 1/4, because remember z was equal to -1 to the 1/4, and since z is equal to e to the I theta, that's e to the I theta divided to the 1/4 power. Yeah, so I made a slight mistake there. Let me just correct myself. Okay. By the way, if I make a mistake, please notify me, right? If I miss something, okay, I just noticed the mistake. Okay, so z is equal to, remember, z was equal to -1 to the 1/4. But since z is also equal to e to the I theta, right? Therefore, I can say that z is equal to e to the 2k pi, right? 2k pi, right? So 2k pi power plus I pi to the 1/4. Okay, 1/4 here. All to the 1/4 power, right? 2k pi is always added to the I pi. Now it's I pi because if you look at Euler's identity, e to the I theta, theta would have to be pi to get cosine pi to be -1, right? For the z to the 4th to equal -1. That's what we need there. And any integer multiple of pi from 2k pi would yield sine to be 0. That's how I know that it's going to be e raised to the 2k pi plus I pi. And then it's all raised to the 1/4 because we took the 4th root on both sides of z. Okay. All right, so this is what we have right now. Okay, the 1/4, I can bring it in. Okay, so now I get z equals e to the whole power of 2k pi divided by 4. plus I pi over 4. And I'm just noting here, it's good to note that there exists an integer k, right? Right? There has to exist an integer k, right? So there has to exist, right? So there exists a k in z, right? Where k is equal to 0, 1, 2, 3, right? All the way up to the n minus 1 integer power, okay, of the exponent. So k equals 0, 1, 2, 3. Again, maximum exponent is 3. It has to be n minus 1 of the original exponent. So if n is 4, it's going to be 3, n minus 1. And then start evaluating at each k value. So at k equals 0, right? So let's start case 1. So case 1 at k equals 0. K equals 0. You're going to notice right away that we get z equals e, k0, it's gone, e to the I pi over 4. Pi over 4, that's z1. That's our root 1. Right, so we found what z1 is. This is multiple roots here. So z1 is equal to e to the I pi over 4. Okay, case number 2 now. Case 2 at k equals 1. You will then get that z2. Okay, so z2 equals e at, let's see, what was it? K equals 1 now. So 2 pi over 4, pi over 2. Pi over 2 plus I pi over 4. Pi over 2 plus I pi over 4 power. Okay, then we have case 3. Case 3 at k equals 2. Then you get z2, z3, sorry. Z3 is equal to e. That's when it's 2. 2 is 4. That becomes e to the pi plus I pi over 4 power. Okay, and then you do the same for case 4 when k equals 3. You get the z to the fourth root. Okay, now these are all called singularities. Okay, I'm not going to finish this problem because it's very long. I want you guys to do it for homework based on what you read on the theory in one of my other live shows or streams. It's on my YouTube thing. I want you to do it, go through it, or it's very good. It has all the theory. You'll be able to compute these. You'll be able to finish the problem. Go through it and see if you can solve this integral. You need to know what the residue theorem is. You need to know what the residue calculations is in order to do this. It's going to be straightforward. And this way is actually faster than the Feynman trick method, right? So there's 2 approaches to this, okay? When it comes to these, you want to be able to choose the approach. It's not always easy. So it takes strong intuition, right? To figure out which way is fastest, but the contour integration is faster, okay? Faster mathematical method to use, all right? Okay, so please do that for homework, either contour integration or Feynman trick. And you can look up both these in my YouTube channel. There are videos for both. Right? You can do a basic practice problem and you'll be able to go through one of these. Okay, as long as you have already found the singularities. Once you have the singularities, use the residue calculation, the poles, right? Residue calculation is in one of my things there. And it's going to explain what to do in one of my videos. And then take from residue calculation and apply the residue formula, 2 pi I times the summation of all the residues of each singularity. And then you'll be able to calculate the integral, okay? All right, I want to show you a visual of this because I believe to develop a strong intuition of whether a problem is solvable and what method to use for a problem, it's always good to see the math come alive. So let's go to the desktop. Okay, let me get out of the shared screen. Okay, and we're going to go to, I think we're going to go over here. So one sec, let me just open a simulation. Okay, so we'll look at a YouTube simulation 1. Okay, so I'm going to open the simulation. Just give me a second. Go back to the desktop. Okay, so 1 second, guys. Okay, just give me 1 second. I'm going to open it up, show you the simulation. It's a really cool simulation. Okay, I'm going to share it. All right, so here is the simulation of that problem that we were looking at, the cosine integral, improper integral of cosine ax all over 1 plus x to the 4. You can see that it's an oscillatory type of kernel, okay, with 1 over 1 plus x to the 4 being some sort of envelope. You should know what an envelope is. If you haven't, an envelope is just pretty much a type of curve, okay, that behaves in an interesting way. So as you can see here, right, we have a graph, right, that shows the value on the y-axis, the x-axis being x, okay, and the oscillatory kernel, 1 all over 1 plus x to the 4, right, has an interesting envelope, right? You can see the integrand of cosine of ax all over 1 plus x to the 4, right? Now, what's the point of seeing this curve here of, of the integrand in our integral? The point is, yes, it looks cool. Yes, it shows, the math coming to life as opposed to me writing down equations all the time. It gives you a geometric understanding of what's happening. That's the most important point, right? And the reason why that's important is because this integral will tell you that, this graph will tell you that this integral is actually converging. Okay, you should know what convergence means. If an integral converges, mean for an integral to converge, it means that it has a value that's finite. Okay, and if it has a value that's finite, you can automatically deduce that it's a solvable open problem. Okay, so quite often, if you're able to graph functions, it's handy. Even if you're not able to graph per se, maybe with graphing calculator or Desmo software, or using another type of software, or if you know programming, that's handy, because then you'll be able to graph models, and the graph will tell you the behavior of the function that you're dealing with, and whether or not you can deduce whether your calculus problem makes sense or not. Okay. So that's why drawing graphs and models or simulations are very handy, and they're cool too. Okay, so you can see this converges, so it's finite. So there is a solution to this open problem. Okay. All right, let's move on from that. Okay, we are going to move on to the second open problem. Now, don't worry, this one I'm not going to go through as much as the other one. Not even close. Well, first off, it's because it's not going to be solvable. Okay, so let me share the screen. Okay, let's go to the entire screen. I'm going to share again, and I'm going to the whiteboard. Okay, let's go to page number 3, problem 2. Okay, so this is another open problem, and let me explain why, as opposed to doing anything. Okay, so if it's improper integral of sine ax dx all over ln of 1 plus x. Now, for those of you who have no idea how to go about this, don't feel scared. Don't feel these problems. The point of these problems is just that, is to get you in a place where you're able to think about how to solve problems that don't have an obvious mathematical approach, mathematical method to them. Method, technique, doesn't matter what you call it. Okay, so anyone have any ideas how we can go about this? I already gave you a hint, by the way, if you were paying attention. I just said that to make sure you guys are paying attention. How do we solve this? How can we solve an integral of this nature, sine ax dx all over ln of 1 plus x? Anyone know how to integrate this? Anybody at all? How to integrate sine of ax dx, ln of 1 plus x. Here, this can throw majority of people off. First off, majority of people will not be able to know how to solve it because they haven't learned the technique of how to solve this. Okay, there's nothing wrong with that, right? You just don't know the technique. Now, for those of you who do know the technique of how to go about this, yes, automatically you will say Feynman trick. Even then, you're going to be wrong. Yes, you will still be wrong if you apply Feynman trick to problem number 2, even though it's a function of the parameter a. Yes, mathematical methods is much harder than what people anticipate. It's not that straightforward, actually. No, it's not. No, it is not. Okay. If you apply Feynman trick to this integral, you go nowhere. Okay, absolutely nowhere. It doesn't work. Doesn't matter what you say, Feynman trick will not work here. Okay. Feynman trick won't work because when you try doing it n number of times, right? In rare cases, you have to do it n number of times, like the other one that I showed you, the other problem. You're going to get something that is, it goes nowhere because you still have to deal with the ln of 1 plus x in the denominator. And how are you going to integrate that with the sign? Okay, so Feynman trick doesn't work. Okay, now as I've mentioned earlier, you probably know, but wait, you may be thinking, Jason, there aren't open problems just hard problems that are solvable that have multiple methods to reach the same conclusion, just using like, your creativity or whatever you want to call it, your smarts or whatever. Yes and no. If you heard what I said at the beginning of what the definition of open means that, yes, number one, you can use multiple methods to the same problem to get the same solution in either method, okay? Or number two, requires immense amount of creativity to come up with something from this out-of-the-box approach to the problem. Or option three, there is no known solution to the problem. Okay, so no, there is no known solution to the problem. So if you thought you can use Feynman trick, you are wrong, right? It would be Feynman trick. You have to use a combination of mathematical techniques is what a lot of people would think when solving this. The problem is those techniques in combination wouldn't make sense still because when you do it, you can try it yourselves for homework. Actually, that's what I'll do. Do this for homework, and I want someone to get back to me actually on it. My contact is www.stem1online.com. It'll be in the link in the description below for this live show for those of you after who watch this. Okay, but yeah, you can try playing around with it, but I can guarantee you that if you play around with this, your approach will be in vain. Okay, you'll just go nowhere. But that being said, that's not the point. The point is not to get a finite solution to open problems. The point is to have fun with it, right? That's the point. The point is to have fun with it. If you're having fun with it, that's all that matters. Okay, and sometimes you can figure out neat things from it. It's like math is not an exact. Well, it is exact, but it's not something that where we follow rigorous rules of known solutions only, right? Unknown solutions are important, actually more important than the known ones. Okay? So do this for homework and let me know what you can come up from that, right? For this integral. So please do for homework, and I want you guys to email me back, okay? And if you still don't get it, you can always book with me an appointment, coaching appointment, where I'll go through what we can do with this integral. Okay, so homework. All right. See what you can come up with this integral. Okay. All right, so we got that. Okay, and what we're going to do, I think, is I want to show you actually a simulation. Okay, we're going to go to a simulation. Just give me a sec. I'm going to show you a really interesting curve here. Okay, another simulation of this function sine of ax all over ln of 1 plus x. I'm going to show you. Okay, so let me just share my screen. Okay, I'm going to share a screen of, yeah, that's what I'm going to show you. So sine of ax all over ln of 1 plus x. So as you can see here, right, this function is a very interesting function, right? So we have an oscillatory integral, right? But you can see our ln of 1 plus x has some decay, has some form of decay with it, okay? What I mean is that there's some sort of exponential decay, as you can see here, right? Now, the exponential curve there, I want to say an exponential curve exactly because we don't have an e here, but you can see that the curve almost replicates something of an exponential decay, right? It's not exactly exponential decay. You can see that it peaks down or sort of, but yeah, my point is that the exponential decay there, right? With ln of 1 plus ln 1 plus x, there's an envelope, and this envelope is, it's stretched or stretched or compressed, right? Based on the scaling, okay? And you can see we have a slow decay for ln of 1 plus x. Okay, so if you look at this, with parameter a being the frequency of sine ax, ln of 1 plus x grows slowly in comparison to the decay, right? And the oscillations from sine ax still actually make this integral converge, okay? Now, be careful. It says it converges, right? I don't want, a lot of people get confused that if a problem is an open problem, and that it must have, if its solution is being infinite. That's not what it means. If it's an open problem, we know that it's solvable, right? Open-ended problem, we know that it's solvable. We just don't have a technique yet to solve the problem, okay? So we just don't have a technique to solve it. That's all it means. However, though, this is another proof that between graphs, models, and certain types of geometries, right, and using programming, that's why programming is really handy, because you can make simulations. It can tell you, even if you are stuck on a problem, what approach to take, or to, sort of question your assumptions, because what this is showing us, right, the mathematical model is showing us, is that this integral does converge. So we know that there should be a solution. We just don't have the technique for it. But even if we do come up with a technique to solve it, there is no known technique at the moment. If we do come up with a technique, we expect it to converge. So we expect the integral to be a finite number. Okay? It needs to be a finite number. It can't be infinite, right? Our model is showing us something that our integral should converge, right? However, we don't have the mathematical methods or techniques to solve this yet. Okay, it is a good challenge problem, though, if we want to try it. Okay. All right, so we're going to look at one last thing in our lecture for tonight. So let me go back again. I'm going to share screen. Okay, let's go back. Actually, just one sec. Let me go to, I can practically open it right now. Yeah, so let me share screen. One of the last things we're going to talk about is this. Okay, just one second. Chrome tab. Just one second, guys. Yeah, we're going to go to the whiteboard. All right, I hope you guys can see this. I am using Microsoft Word right now, okay? And the point of using Microsoft Word is because I want to talk about the applications that can arise from open-ended problems, specifically in ODEs, ordinary differential equations, and in advanced physics, actually. Okay, so there's applications here. So let's talk about that. That's what makes this stuff more interesting. If we talk about the applications, most of the times, what helps people is maybe having some sort of relationship to the real world, right? And then it makes more sense intuitively, anyways. Okay, so we're going to talk about the physics applications. Okay, so we're going to pretty much expand or extend open-ended mathematical problems into ODEs and directly into physics, okay? Instead of just solving the equations mechanically, right, for known solutions, right? We're going to focus pretty much on the structure, okay? The natural structure, the natural structure of the world, pretty much, right? Okay, natural physical structure of the world. Okay, and how ODEs come into play with this. All right. So when it comes to, for instance, right, some things that are going to be emphasized that I want to emphasize, right? Conservation laws, right? You don't need to know what conservation laws are per se. You can look them up, right? But quite often, conservation laws are going to produce certain types of ODEs, differential equations. Symmetry is another one. Scaling is another one, right? Certain types of behavior of the models, right? So one model, you may have a growth or decay or oscillation, right? These matter for a lot for closed, if our integral is a closed form or whatever, right? And how the same ODE actually appears in things like mechanics, diffusion, or in quantum models, okay? Now, again, as I mentioned, when it comes to anything that's open-ended, it is going to have to be open-ended. The goal is not to compute, okay? In mathematics in general, the goal is not to compute, okay? The goal, especially in this lecture, what I'm talking about, the goal is to learn how to recognize specifically what mathematical method to use to solve an open-ended problem, okay? Or in this case, right, what we're talking about right now at this moment, when it comes to ODEs, right? When to recognize that an ODE appears in a specific physical framework, okay? And how to reason about its behavior, okay? And so this was going to really help, and this is my what do you want to call it? My unique perspective to doing math, right? Developing critical thinking, your applied mathematical intuition or physical intuition, okay? And, transferring problem solving skills, right? Across calculus, ODEs, and physics, okay? That's the main goal of this, right? Actually, of all of my lectures, pretty much. Okay, 1 second. See if anyone is sending me something here. So I make sure. Let me see if anyone's coming in. All right. So we're going to be looking at this guy right here. Okay. So this open-ended physics problem. Okay. Let me see if anyone is coming in. I want to see if anyone's coming in at the moment. Okay, we're still at the same amount of people. All right, so we're looking at this. Okay, we're looking at the bottom part of the Microsoft Word document. So it says here, a particle moves in one dimension through a resistive medium. Okay. And we know that there's experimental evidence that suggests that the resisting force depends only on the particle's velocity and always opposes the motion. Okay. So we want to use some form of physical reasoning to propose a differential equation governing the motion. That's number one. Number two is to identify which conservation or balance principle justifies the model. Okay. Number three, without solving the equation explicitly, describe any long-term behavior of the particle. Four, discuss how the same ODE structure could appear in heat flow or quantum damping. All right. So we want to be able to come up with some sort of DE, differential equation governing the motion, based off of this problem here. Okay. Now it helps if you've taken some type of physics background here, right? Because we're talking about forces. Okay. So you can see that the particle moves in a one dimension through a resistive medium. Okay. And we want to take that and suggest that the resisting force depends only on the particle's velocity and always opposes the motion. Right? So here we're going to use some physical reasoning about the natural world and come up with a mathematical equation or mathematical model that makes sense. In this case, it will be a differential equation. All right. If you have any ideas. Okay. So what we can do is, right? Oh, let me get out of the whiteboard. Sorry about that, guys. So let's look at this again, right? So we need to use some sort of physical intuition to determine the differential equation of the motion. Okay? That's the first thing that our question is asking. Okay? So what do you think we can propose here? Let me just take this down. So that's why I have if I have to go to the whiteboard. So let's go to the whiteboard. Okay. Maybe take a picture down if you need to refer to it whilst I'm doing it, because I'm gonna get out of the share screen and get to the other share screen. Okay. Going to get over here now. Okay, so let me take out. Let me see. I'm going to stop. Yeah, I'm going to stop sharing. I'm going to go to stop sharing. I'm going to go to the whiteboard. Okay, let's go to. Yeah, I'm going to go. And then I'm going to go to the whiteboard. Okay, so let's go to another page here. Okay, we're looking at the differential equation that can be formed with that. Just 1 second, guys. Okay, so we're looking at that problem. So looking at another problem 2, problem 3. Problem number 3. So what we can do is, right, remember, we want to be able to come up with a differential equation. We know that our particle moves through a medium. We know that they suggest that there's a resisting force depending only on the particle's velocity. So it's good to draw these, as I always mention, whether it's for mathematical intuition, the same for physical intuition. We want to be able to draw things. We draw things, we can see what's happening. We see what's happening, we see the behavior of what's happening, and then we assign quantities to what's most appropriate to the model that will make sense, and then we can transfer that into an equation. Okay, so let's do that. So let's say we have a particle here. Here's my particle P. Okay, I have my particle P. And we know it moves in one dimension. Right, it moves in one dimension. So let's say we have, something like this. Okay. Just so that's going in one direction, in one dimension. And has a velocity, this particle has a velocity v. Okay, so velocity v for velocity. But as that particle is moving in a one-dimensional framework, it's also experiencing some sort of a resistance force against the particle. Okay, so if there's a resisting force against the particle, the force is opposing the velocity. Okay, so we know that there has to be some sort of force. I'm going to call it, so in second. Yeah, let me use, there it is. Sorry about that, guys. I'm going to call this, I'm going to call this F. Okay, so let's call this force F. Here's F. So it's resisting. Now, we know that, let me think here. And therefore, we know that if you know any physics by any chance, I assume most of you have taken physics. There's something called Newton's second law, which states the following. Okay, Newton's second law states that the sum of all forces is equal to the mass, okay, mass times the acceleration. Okay, this is by Newton's second law. Okay, this is Newton's second law. Newton's second law. Now, another thing too is that since we know that we're dealing with a differential equation model, okay, I want to use for this. Let's use blue and green. Okay, I'll use green here. So sum of all forces, right? Sum of all forces is equal to ma. Now I can change my a. My a is the second derivative of the position, or the first derivative of the velocity with respect to time, right? Because this particle is moving with respect to time. Everything is with respect to time, right? So in reality, what we have here is m dv dt, right? So m times dv dt, right? So dv dt. Okay, so we have this. So we know our framework has something to do with this relationship. Okay, I just put it in a differential form. Now what I can do here is sum of all forces acting on the particle. There's only one force, F. Okay, so I'm calling this F. You don't have to say anything else, but F is going in the opposite direction. Okay, so it's going to be negative. By the way, it's good to always direct which way will be positive and negative. This is positive x to the right, upwards is positive y. So left will be negative. Anything to the left in the x direction will be negative, so the force is negative, so negative F. And then this will be equal to m dv dt. Okay, so now we got m equals m dv dt. Okay. Anyone has any questions? Right, so this is what we've got right now. Okay. This is our m dv dt. Now, there is one thing I want to mention. Okay. This would be negative F. So again, we need to, there's still an issue, right? Because we know that the force is supposed to be going against, right? Going against the direction of motion of the particle, all right? there's a resisting force. Now it always opposes the motion, okay? So we get negative F equals m dv dt. Anything else that we can infer from this? Well, that F, right? F here, if this is negative F equals m dv dt, right? F is resisting, is the resisting force, okay? I noticed I made a mistake somewhere. So in order for this particle to move with a velocity v, okay, let me see, I think I made a mistake somewhere. Let me think. Resisting force, vdt, mdv dt. Net force is mass of acceleration because we have a force present, so we have to use Newton's second law, ma. Then after particle p moves with a velocity v to the right, and as it moves to the velocity v to the right, there's a drag, there's a force that's resisting it. We're gonna have that velocity v. Is that a change in? That's what we have to ask, if there's a change in velocity. If there's a change in velocity, there's an acceleration. If there's an acceleration, there's a force being applied. But if that's just constant velocity, then no, we have to worry. Then there's zero acceleration going to the right, and the only force is applying for is from the right. Is that force the velocity coming from the left of the particle? If it's a constant velocity, zero acceleration means zero force from the left. Yeah, so this is fine. So negative F equals m dv dt. Okay, this is what we've got. All right, now the model, okay, the model can be tricky to sort of transcribe what to do, if you know what I mean. Okay, right. So you can see that, right, we have a resisting force, right? According to the problem, resisting force on the particle's velocity is always opposing the motion, right? Let me see here, v. Because then we get this. Now, yeah. So this force, I want to say here, yeah, that's what I want to put here. I want to say that F, so we know what F is. This is negative F, okay? This is negative F because it's opposing the direction of motion of the velocity of the particle. Now F is equal to, let's see, dp dt, f dt, dp dt, dp. I think we can say something about the impulse. No, we don't, because we don't have any momentum here. Do we have momentum? Oh, wait a minute. Just 1 second. Now, this is interesting. Anything to do with the momentum or change in momentum, which would be the impulse of the particle. Because the negative F equals m dv dt. Yeah, I'm thinking about probably taking out, because F can be, first off, F is a function of time. That's another thing too I'm going to put down here, so that's why it's not confusing what F is. It's very important to say what it is. F is a function of t. Okay, and then this is equal to the m dv dt, or m dv dt. Okay, because it's a function of time. Yeah, this would be fine. F is equal to also m times by a. Just 1 second. If I could represent F with anything else, the force is not retarding. I don't think it's retarding because it just says it's resisting according to the problem. Just 1 second. I want to make sure it is. One second. I think it is. Actually, yeah, it is retarding. Let me explain what I mean by that. Okay. So if the particle P is moving with velocity V, okay, as we said from left to right, okay, it's moving with a constant velocity V. However, though, there is a force coming from the right that is resisting the particle's velocity. So that force that's resisting the particle, actually, when it resists, it has something called a retardation force. Okay, so it's actually retarding. In other words, what that means is when you have a resisting force or a retarding force, it should produce negative acceleration. Okay, why would it do that? Well, it just means that the object is slowing down. So in this case, yeah, the question was saying that there's a retarding force, right? Because it's resisting. Okay, so in reality, if we have a retarding or resisting force, that means that the object on the other end that's going against that force would be slowing down, producing negative acceleration or deceleration of the object. Okay, so in reality, let me go back here. So let me see, that force equals mass and acceleration. Yes, that's true. V equals, so this should be actually negative F. I'm going to put something here. Let me just, this is going to be negative F. Yeah, negative F. I'm going to put over here negative. So negative parentheses, F minus KV, okay, equals M dV dt. All right. Now, let me explain what that is, okay? You guys know what net force equals M dV dt is, Newton's second law. However, though, since there's a resisting retarding force, which is opposing the direction of motion of the particle's velocity, since there's a retarding force in the opposite direction, that means that it's inducing a negative acceleration on the object. So it's decelerating. And anytime when you have that, a retarding force, you have this this drag. You have F being the force, V being the velocity, K being the, what's it called? Like a retarding coefficient, right? So K, let me put here, K is the retarding coefficient. Retarding coefficient. Okay? So the F minus KV. So that's what happens. We have to put that negative KV into our force equation, okay? And so it's F minus KV is M dV dt. And it's negative the whole thing because of the resisting force going the opposite direction on the x-axis, horizontal axis. Okay? So if we were to FOIL that out, okay, you'd actually just be getting like KV, right? You just get this right here, KV minus F, right? Because the negative is positive, and this is equal to M dV dt. That's our differential equation that we have to deal with, okay? All right, so we have that. And so that's one of the things that we have. So we have the resisting We're dealing with the resisting retarding force. Okay. Now, part two was to identify which conservation or balance principle justifies it. As I said, I pretty much already answered that. Um, since it's a retarding force, we know that it has to be it has to produce a negative acceleration, so it has to be in the form F minus kv equals mdv dt. That's a modified form of Newton's second law when we have a resisting force. Okay, so this model justifies it. All right. Number three, without solving, explicitly describe the long-term behavior of the particle. So long-term behavior, what we can see here, right? So what do you think the long-term behaviors would be for this? Anybody? Long-term behaviors of our physical model. Long-term behaviors. So think about it. That's what I want you guys to think about for homework. What is the long-term behavior for this model? Okay. So long-term behavior, homework, and without solving it. Okay. I want you guys to produce. So a lot of times when it comes to math and physics, as I said, it's not just about solving something numerically. It's about building the correct problem-solving intuition for the problems. Okay. So I want you to figure out part three, long-term behaviors. What are the long-term behaviors? Behaviors of the model. If you have any questions, you can always ask me in my email, right? www. Oh, not email, but my website, and then you can forward it there. I'll respond to anyway. Again, it's in the link below. Okay. All right. Let me see if we're going to discuss anything else. I think that is it for tonight. I'm getting tired. Yeah, I'm getting tired. All right. So let me see here. Yeah, I think that's going to be it. Okay, so let me just get out of the share screen. Okay. Yeah, I think that's going to be it for tonight. This was really good. I hope you guys enjoyed it. Stay tuned for much more stuff, much more interesting stuff. Again, before we wrap up, though, I do want to mention something that is very, very important. Okay. I want to say this clearly, okay, because it is really important, and it will help you really grasp these concepts. Why is someone giving me? Sorry for that. Someone's texting. So if what was I saying? If tonight if tonight helped and you feel less lost about how to handle and distinguish a hard problem, that's not just luck, right? That is actually a trainable skill. I'm actually making you guys learn a very interesting skill. It's something called creativity. Okay. So the exact reasoning, right? The exact reasoning style that we practiced, right? That we practiced tonight, actually, slowing down, spotting the structures, testing ideas, testing different methods, is what I built systematically again and again in my book, Advanced Integration Techniques. Okay, which is specifically for strong, you know, if you're a high school student, then really strong high school students, but also strong undergraduate students, right? Who want challenges and to build their calculus intuition. Okay. And if you want to develop, right? If you want to develop any of your develop this skill with guidance, right? Because it is a skill. It takes a while to develop, and sometimes you may need extra help. Um, if you want to be able to develop the skill and not just solutions that accidentally you just came across or you memorized, that's not real learning. If you want the actual skill, then maybe a skill with guidance that you get with guidance. Uh, you can get that with real mathematical thinking. Okay. Uh, right. So I also want to just tell you and let you know, right? You can work with me one-on-one for with students when it comes to calculus, ordinary differential equations, or any physics course for that matter. Okay, if you want to build these types of skills, and they're invaluable skills regardless of the course. Okay, so the goal is not to do more problems, right? As I've mentioned, is to be the kind of student who knows how to approach them really creatively. All right. So my point is to think clearly and solve confidently. Right. Again, you can get my services, my coaching services, in the link below, or you can purchase my book. Also link below. Both the ebook and or the physical copy is available. All right. Stay tuned for more streams and live shows. Again, I'm available. My live shows are Wednesdays at 8:30 p.m. Eastern. Streams are Thursdays at it was around 7:30 p.m. Eastern. Another stream on Sundays at 7. Was it at 8 p.m. Eastern streams? But the live shows is when I should be telling you guys when I'm around. Stay tuned for more interesting mathematics lectures, streams, and live shows. There'll be plenty of more interesting stuff coming soon. Have a good night, guys, and see you next time. And don't forget to like and subscribe. Bye-bye.